In the last lesson, we looked at the two types of basic design of air temperature measurement devices. These were the direct reading type and the remote reading thermometer. Both types are subject to the three errors of all air temperature measurement instruments, which are instrument error, environmental error, and heating error. Heating error is caused by the movement of the aircraft through the air. The air temperature rises in the immediate vicinity of the aircraft as a result of friction or kinetic heating, and air compression or adiabatic heating. Kinetic heating is the main contributor to the temperature rise effect in the direct reading thermometer. As the speed increases, more and more molecules of air per second impact against the flat plate at the front of the probe. This causes a temperature rise due to friction. Adiabatic heating is the main contributor to the temperature rise effect in the remote reading, or total head, thermometer. It is caused by a conversion of energy, not a direct application of heat. For example, boiling a kettle is a direct application of heat, whereas pumping a bicycle pump causes a rise in temperature without any input of heat because pressure energy is converted into temperature energy. In the remote reading temperature probe, the outside airflow, which may be several hundred knots, is brought virtually to rest in the platinum measurement chamber very rapidly. The energy of the moving air is released in the form of a temperature rise. This is adiabatic heating. Let's show these combined effects on a graph. The y-axis represents temperature, and the x-axis represents the aircraft's speed. The temperature of the undisturbed air through which the aircraft is about to fly is what we are trying to measure. We call this the static air temperature, or SAT for short. In formulae, it is often written as T subscript S. However, the effect of the heating error is to cause too high a temperature to be measured. If there were no losses in the measurement process, we would measure total air temperature, otherwise called TAT. The difference between static air temperature and total air temperature is called total ram rise. There is a known relationship between the relative speed and the temperature rise. The laws of thermodynamics are such that the combination of kinetic and adiabatic heating will always add up to total ram rise. Total air temperature is defined as the maximum temperature attainable by the air when brought to rest adiabatically. And in formulae, it is often written as T subscript T. Unfortunately, any measurement process always has leaks and inefficiencies, so we do not measure the full ram rise. The amount of ram rise actually sensed is called the measured ram rise. If we could measure the total ram rise, we would measure the total air temperature. However, in practice, what we measure is the ram air temperature, which is lower. The ratio of the measured ram rise to the total ram rise is called the recovery factor. Suppose that, because of losses and inefficiencies in measurement, the measured ram rise is only 90% of the total ram rise. In this case, the recovery factor would be 0.9 or 90%. In formulae, the recovery factor is often written as K, or K subscript R. Let's see how these definitions interact. We'll assume an aircraft experiencing a static air temperature of -60 degrees Celsius at a speed where the theoretical total ram rise would be plus 13 degrees. Assume a recovery factor of 0.9. The static air temperature is -60 Celsius. The total ram rise is plus 30 degrees. Remember, this is a theoretical figure and cannot actually be achieved. The total air temperature would therefore be minus 30 degrees Celsius. The recovery factor is 90%, which is expressed as 0.9. Therefore, the measured ram rise is total ram rise times 0.9, which is plus 27 degrees. Applying plus 27 to minus 60 gives us a ram air temperature of minus 33 degrees Celsius. This is the figure which you would actually see on the ram air temperature gauges. You would then use one of several methods to arrive at your correction factor of minus 27 degrees, and then apply it to get the static air temperature, which is what you want. Theoretically, uncorrected air temperature gauges give ram air temperature, not total air temperature. However, in many aircraft, the gauge is incorrectly labelled TAT. What you see on the gauge is sometimes called indicated outside air temperature, or IOAT. Static air temperature is sometimes called corrected outside air temperature, or COAT. OAT on its own stands for outside air temperature and is usually taken to mean SAT. The relationship between them is that total air temperature equals static air temperature plus ram rise. Static air temperature is always colder because total air temperature has undergone heating, and so ram rise is always positive. Or indicated outside air temperature equals corrected outside air temperatures plus ram rise. The indicated temperature can be converted to static air temperature by the following methods. The rapid formula for practical use in the air, the navigation computer, the accurate formula which you will need for exams, data tables, and the air data computer. There is a rapid formula for use in the air. It is simply that the ram rise equals your true airspeed in knots divided by 100, all squared. So that if your TAS is 200 knots, the ram rise is 4 degrees. And if your TAS is 300, the ram rise is 9 degrees. And so on. This formula should not be used in exams because it is not quite as accurate as the computer solution. But it is good enough for practical use in the air when a quick solution is required and it is not convenient to find a nav computer or look up tables. The nav computer is the recommended way to find ram rise in exams and is used in multi-crew aircraft if no air data computer is fitted. On the slide rule face of the nav computer there is a blue scale. The outer scale is true airspeed, and the inner scale is ram rise. If the TAS is 400 knots, the ram rise is plus 17 degrees. The accurate formula may be the only way of solving some exam questions. It is also the basis on which the navigation computer, the tables and the air data computer solutions are calculated. The formula is that static air temperature equals the total air temperature divided by 1 plus 0.2 times Kr times the Mach number squared. In the context of this equation, TAT is actually RAT, as is often the case. This is the temperature that you see on the gauge. Kr is the recovery factor. On most modern aircraft, it is usually very close to 1. Mach number will be explained in a later lesson. It is a measure of your speed compared against the speed of sound, and is indicated on an instrument called a Mach meter. Before we continue with a worked example, we need to explain that both SAT and TAT in this equation are in degrees absolute, or Kelvin. When Celsius designed his temperature scale, he chose the boiling point of water as 100 degrees Celsius and the freezing point of water as 0 degrees Celsius. This seemed reasonable, given the state of physics at the time. However, the problem with normal Celsius temperature scale is that it changes sign at 0 degrees Celsius, the freezing point of water. Numbers above 0 are positive, whilst numbers below are negative. But to measure the relative levels of hotness in objects in a meaningful way, we should start from a baseline of absolute 0, no heat at all. This occurs at minus 273 degrees Celsius on the Celsius scale. So, minus 273 degrees Celsius is 0 degrees A or 0 K on the Kelvin scale. 1 Kelvin, or 1 degree absolute, is the same amount of temperature change as 1 degree Celsius. Therefore, the freezing point of water occurs at 273 K, the boiling point of water at 373 K, and so on. Now, let's try a worked example. You are in a Boeing 737 and your indicated TAT is minus 20 degrees Celsius. The Mach number is 0.73, which is a typical speed for a Boeing 737 in long-range cruise mode. The recovery factor is 0.98, which is a typical value for a modern TAT probe. The value for Kr, the recovery factor, is determined by flight testing and is published in the operating instructions for the aircraft. The TAT is minus 20 degrees Celsius. This is the same as 253 kelvins, or 253 degrees absolute. Now we substitute into the formula. The TAT is 253. Kr is 0.98. The Mach number is 0.73. If you get your calculator out and do the sums, you'll find that this works out as 253 divided by 1.1044, which is 229. So the static air temperature is 229 kelvins, or degrees absolute. This is the same as minus 44 degrees Celsius. So we have used this formula to go from a total air temperature of minus 20 to a static air temperature of minus 44. This has shown you how to use the equation, which you need to know for the exam. However, airline pilots do not really do these sorts of calculations in flight. In practice, in older aircraft, they would use tables. And in newer aircraft, the air data computer would do it for them. This is an example of the correction table for the Boeing 737. Again, we'll show how it works and we'll use the same numbers. You enter with the left-hand column and go down to the indicated total air temperature, which is minus 20 in our example. Then, in the Mach number row, you find 0.73. You read off the static air temperature where the row and column meet. As we can see, it gives the same answer, minus 44. However, any large airliner less than 20 years old or thereabouts will have an air data computer. We will look at this device in more detail in a later lesson. The ADC is a computer that takes inputs of pitot, static, angle of attack and TAT and processes them to calculate airspeeds, altitude, Mach number, TAT and SAT. The static air temperature is therefore automatically computed. The majority of the aviation world uses centigrade or Celsius as a temperature scale, but Fahrenheit is still widely used in the USA. There are 9 degrees of Fahrenheit temperature rise to 5 degrees of the equivalent Celsius rise. And 0 on the Celsius scale is plus 32 Fahrenheit on the Fahrenheit scale. There are formulae for conversion, but for simplicity, use the temperature conversion scale on the CRP5. Let's summarize what we've covered. Heating error is caused by the movement of the aircraft through the air. Kinetic heating is the main contributor to the temperature rise effect in the direct reading thermometer. Adiabatic heating is the main contributor to the temperature rise effect in the remote reading, or total head, thermometer. The static air temperature is the temperature of the undisturbed air through which the aircraft is about to fly. This is what we are trying to measure. The heating effect would give us total air temperature if the measurement process were 100% efficient. The difference between the static air temperature and total air temperature is called total ram rise. The laws of thermodynamics are such that the combination of kinetic and adiabatic heating will always add up to the total ram rise. However, because of measurement inefficiencies, the measured ram rise is less than the total ram rise. What we see on the gauge is the ram air temperature. The ratio between the measured ram rise and the total ram rise is called the recovery factor. The indicated temperature can be converted to static air temperature by the following methods. The simple formula should only be used in the air. It is not accurate enough for exams. The nav computer is the recommended way to find ram rise in exams and is used in multi-crew aircraft if no air data computer is fitted. The accurate formula may be the only way of solving some exam questions. It is also the basis on which the navigation computer, the tables and the air data computer solutions are calculated. It uses the Kelvin or absolute scale. In practice, tables are used on older aircraft. And the air data computer gives a direct readout of static air temperature on more modern aircraft. If you have to convert Fahrenheit to centigrade, use the navigation computer. This concludes the lessons on temperature measurement. The next lesson will go on to consider the air pressure instruments.